It was a pleasure to be joined by Professor Francis Livens for the first instalment of the RADNUC WebSeries. Francis Livens is a professor of radiochemistry at the University of Manchester, where his research is focused on environmental radiochemistry. This describes the study of radionuclides in the real environment, including how radionuclides interact with microorganisms and minerals in the environment. Additional to his academic work, Professor Livens is also director of the Dalton Nuclear Institute, non-executive director of the Nuclear Decommissioning Authority, member of the Nuclear Innovation and Research Advisory Board to Government, and member of the Independent Advisory Panel to the Office for Nuclear Regulation. It was a great honour to have Francis talk us through the basics of nuclear energy, covering topics like what is nuclear fission, how can we use it to produce energy, the history of nuclear energy, and how nuclear energy fits into our modern world.
Good morning, Francis.
Good morning.
How are you?
I'm good. Looking forward to this.
Yes, me too. I'll start with a really broad question. So, what is nuclear fission and how does it liberate usable energy?
Okay. So, nuclear fission is a property of some of the heaviest elements that we know. In nature, uranium, but also manufactured over the last 70 or so years, plutonium has this property. And what happens is that you can make these very heavy nuclei split into two fragments. And in splitting, they liberate a lot of energy. That energy becomes manifest as heat. You can take the heat out of the nuclear reactor and you can use it eventually, as we usually do, to make electricity. And the fission process itself is triggered by a very small particle called a neutron, which hits the heavy atom, starts it vibrating vigorously, and eventually that vibration is so vigorous the atom splits into the two fragments. That's when you get your energy. But also that splitting process liberates a couple of further neutrons so they can go on and propagate other generations of fission reactions. So it has the possibility to be a self-sustaining reaction.
Right, and that brings us nicely onto the concept of criticality. So when we hear the word criticality, we instantly assume something bad. What does to go critical, what does that mean?
All it means is that the arrangement that you have assembled is such that you have a self-sustaining reaction, because I've just mentioned neutrons. If too many neutrons leak out, every fission uses up one neutron to trigger the fission. So for the reaction to be self-sustaining, at least one of the neutrons produced in the fission process must go on to propagate a further fission reaction. Because if less than one neutron per generation propagates fission, then the reaction will just run out of steam and it'll stop. So that's a subcritical arrangement. And if exactly one neutron per generation goes on to propagate fission, that's a sustainable arrangement. You have a steady state, and that's what you seek to achieve, say, in a nuclear power reactor. If you have more than one neutron per generation going on to propagate fission, then the reaction will run out of control, and that is an atomic weapon or a reactor accident or a criticality accident, all of which are very bad things. So criticality is a function of the quantity of material you have. If you've too little material, then too many neutrons will leak out and you can't possibly have a self-sustaining reaction. The physical arrangement of that material, because if you make it a very inefficient shape, a very flat, thin plate, for example, lots of neutrons will leak out. A sphere is a much more efficient shape. And the presence of other materials in there that absorb neutrons and don't allow the fission reaction to happen. So criticality itself is what you're seeking to achieve in a nuclear reaction, but it's quite a complicated thing to achieve. The physics is complicated, the engineering is complicated.
Right, okay. And is that the reason why in reactors we have fuel pins as separate rods of fuel?
It's part of the reason. You have the arrangement you have the arrangement of the fuel in the reactor. You often have a material called a moderator in there. And what the moderator does is it fine-tunes the neutron energies, because the neutrons that are produced in fission are highly energetic. And you need to take away some of that energy to increase the probability that they'll go on and propagate another generation of fissions. So the neutron comes out from a fission reaction, it interacts with the moderator, it's slowed down, and that optimizes the chance of it then propagating another fission reaction. So in a reactor, you have the fuel, which is where the reaction happens. You often have the moderator, which is fine-tuning the neutron energy. And you'll also put in control rods, which are neutron-absorbing materials. So if your reactor has got, say, fresh fuel in it and is getting all a bit excitable, then you put the fuel rods in and they absorb some of those neutrons and calm the reaction down. So the control rods are the equivalent of, say, the accelerator pedal in a car.
Right, okay. And to initially get our first criticality, where does the first neutron come from? How do you kickstart that reaction?
Okay, well, there are always neutrons floating around in nature, from cosmic rays, from small amounts from naturally radioactive materials. But if you want to start up a reactor, you can just buy a neutron source. It's not that easy to be given permission to buy one, but you can. And these are mixtures of materials like americium, which is a very intense alpha emitting nuclide, and beryllium, which is a light element. And americium, beryllium has the property where if an alpha particle hits it, then it'll undergo a nuclear reaction and actually emit a neutron. So you can get these little things, which are about the size of the end of your finger, and they're a mixture of americium and beryllium in a steel capsule, and they're chucking out loads and loads and loads of neutrons. So they're the equivalent of, I don't know, the spark plug in a car. You put one of them in your core when it's just ready to go, it gives it a little pulse of neutrons, and off you go.
Okay, brilliant. And do they incorporate that into the fuel assembly, or is it just added into the reactor separately?
It's a separate thing.
Okay.
So it's just a little device that you can put in and you can withdraw once the reactor's up and running. It doesn't need the extra neutrons anymore.
Right. Okay. Got it. And I've got one of the questions on my notes is fissile versus fertile ? So different reactors can use, I know that there's some reactors that can use natural uranium. What's the difference between fissile and fertile?
Okay, so, right, fissile material is material which can undergo fission with thermal neutrons. So these are neutrons which are in thermal equilibrium with their surroundings. So in a reactor, they've been produced, they've interacted with the moderator, they've calmed down to this thermal equilibrium, and those neutrons can interact with some forms of elements which will fission. So uranium-235 will fission in those circumstances, plutonium-239 will fission in those circumstances. But uranium-238, which is actually the dominant uranium isotope in nature, will not fission if it's hit by a thermal neutron. So uranium-238 is not fissile. But what it will do is it can absorb that neutron. So it becomes uranium-239. Uranium-239 then undergoes a couple of radioactive decays, fairly short ones, and becomes plutonium-239. So you've converted a non-fissile uranium-238 into a fissile plutonium-239. So an element like uranium-238 that can be converted into a fissile isotope is called fertile. Uranium-238 is one example. Also, thorium-232 is another example.
Okay, and do all thorium reactors operate on the basis of fertile fuel, or is there some fissile isotopes of thorium as well?
Well, you have to have some fissile content because otherwise your reactor won't go. You need the conversion of a fertile atom into a fissile atom uses up one neutron, but it doesn't give you any neutrons. So to create fissile material through this process, which is sometimes called breeding, you need neutrons that are perpetuating the fission reaction, because that's keeping the reactor going, that's continuing to give you your neutron population. And you need so much of that neutron population that you can afford for some of it to be absorbed by the fertile atoms and turned into fissile atoms. So you couldn't make a pure thorium reactor in the way that you can make a pure uranium reactor, because natural uranium contains a bit of fissile 235 and a lot of fertile 239. In thorium, there is no equivalent in natural thorium of the fissile 235. You have lots and lots of fertile, but you need something else, which they'd call a driver fuel, to make the reaction go and give you the neutrons to convert the fertile thorium 232 into fissile U233.
Right, and that driver fuel would not be thorium. There's no fissile isotope.
You can't. Well, not in usable quantities. So it would be something like enriched uranium or plutonium.
Right. Okay. Cool. One of my questions is, when was fission first used to generate electricity? So I've been doing nuclear for a while, and I still get this question wrong in Christmas quizzes. What was the first nuclear reactor?
The first nuclear reactor wasn't used for generating power at all.
Okay, let's start. You brought on to a nice topic, actually. Yeah. Okay, let's start with, what was the first reactor?
Okay, right. So the very first reactor was entirely natural. It was a very rich uranium ore deposit in Oklo in Africa, which became so. It was in a geological setting where actually you just had a natural fission reaction running, and this was from memory 1.5 billion years ago or something. But that's the first known example of fission reaction on Earth. Getting a bit more up to date, the driving force for nuclear technology was the wartime atomic bomb project, and there were a number of attempts at experimental reactors. Some worked, some didn't. I think the first one that's generally felt to have been a sort of working nuclear reactor was the Chicago Pile at Argonne. Scraping a bit around in my memory here. And that was really to demonstrate the technology. And that was followed very rapidly by some production reactors, which were built out at Hanford in Washington State, which were designed to convert uranium into plutonium, which could be separated to make the first atomic bombs. And the military use of nuclear power was really what drove the technology for the first, through the 1940s and into the 1950s. In the 1950s, the Russians demonstrated that you could take the heat from a nuclear reactor and make electricity by hooking up a fairly small reactor to the grid, but that was done in 1954. And then Calder Hall in the United Kingdom is often taken to be the first commercial nuclear power station, because that was designed to put significant amounts of electricity into the grid, though it was also designed to produce significant amounts of plutonium for the military program.
Right, so that's a long time ago. That's 70 years of nuclear technology that we've had.
Yes.
Yeah, a long time to develop the technology. So that kind of brings me on to the next part, which is, how does it compare with other energy sources, namely wind, solar, and gas? So,
I think one of the things that's both been an advantage and a disadvantage for nuclear is that we've always been aware that nuclear waste is really bad stuff. So we have always been interested in the whole life cycle of the technology. And if you contrast that with, say, our use of fossil fuels, where we haven't been interested in the whole life cycle of the technology, and our interest in it ends where we put the CO2 up the flue from the central heating boiler or out the exhaust pipe of the car and into the atmosphere. And we've been doing that for a couple of 100 years. And now I think we're starting to see the consequences of that, because we're recognizing that continuing to do that leads to adverse consequences. So in some ways, all the detriments and costs of climate change reflect the fact that we have never looked at the whole life cycle of fossil fuel as an energy technology. And we're starting to do that with, for example, carbon capture and storage as a technology that we're starting to look at. And it's a bit similar for me with renewables like solar or wind. So, solar panel manufacture uses scarce materials. It's a pretty messy process. Those panels have a fairly limited life, and then you have to do something with them. And none of that's particularly well thought through. Similarly, wind turbines, it's far from clear how much of those can be recycled at the end of their 20, 25-year working lives. So, for me, there is no energy source available that provides the energy we want or we require in the quantity we require it, which doesn't have some sort of environmental impact or detriment. It comes down to a question of what is the form of that detriment that you're prepared to accept. And then there are other benefits and disbenefits. Like, people will always say, well, the renewables are fine, but the wind doesn't always blow and the sun doesn't always shine. So there's an argument for nuclear as base load. And probably there is a mix of, you could do a lot with renewables, particularly in the UK with wind, but you can't do everything. And the other thing I think that people lose sight of is, if we seriously replace fossil fuels in our energy mix, the quantity of alternative fuel that we are going to require will be massive. So, for example, you could easily see a 4 or 5-fold increase in electricity requirement if we went to electric heating in our houses, electric propulsion for vehicles. And that suddenly becomes a huge number of windmills or an enormous area of solar panels. So that is a problem, because renewables are low energy density. And the other problem is that they give you electricity. That's what they do. There are some processes that are really not designed to use electricity. So there are some very difficult to decarbonize bits of our society, particularly things that require high temperature processes: cement manufacture, glass, ceramics, steel. Those sorts of processes require very high temperatures, which would be very difficult to generate if all you had was renewable generated electricity. And this is where there is interest in advanced nuclear technologies, which are capable maybe of giving you a stream of helium gas at 900 or 1,000 degrees, which is maybe a better thing for some of these hard to decarbonize industrial processes.
So the obtaining heat, you mentioned helium gas and heating it to 900 degrees. Obtaining heat in that way from a reactor, would that be alongside using water as a coolant, and then you'd also have a helium coolant? Or are these advanced reactor technologies using exclusively helium?
It would just be helium. So you have a reactor core that's running at high temperature. You just push helium through it. It comes out at 700, 800, 900, depending on your reactor design.
Right. Okay. And these sorts of reactors, do they currently exist, or are they concept?
Some certainly exist in China and Japan. They're so-called high-temperature gas-cooled reactors. They exist. The Japanese one and the Chinese one have both operated pretty successfully. It's certainly a technology that could be developed and deployed. And there are many other variations on advanced reactors that can give you attractive outcomes as well. Again, some of those have been demonstrated. Some are still much more ideas, but could be developed and demonstrated. So there's a whole host of different ways of using nuclear that's out there that we could start to adopt if we wanted to.
Right, but the current technologies use water and they're exclusively generating electricity.
Yeah, the current technology is very much optimized for generating electricity, and with the exception of our rather old advanced gas-cooled reactors, which use gas to take the heat out of the core, but then use the hot gas to make steam to drive a turbine to make electricity. Pretty much the standard approach to nuclear technology is a water-cooled reactor, which then generates steam to make electricity. And they're not ideal for other purposes because they're optimized for steam. They actually often run relatively cool, sort of 350-ish degrees. And if you ran hotter, like the high-temperature gas-cooled reactors, there would be other things you could do with that heat.
Okay, cool. And the government has got a pretty ambitious plan with our current nuclear reactors that they want to expand the use of nuclear energy in the UK. It's a technology that we've been using we mentioned, for almost 70 years now. Are there any big challenges in the way of nuclear, in the way of this plan? And are these challenges regulatory, technical, economical?
All of the above. I think the simplest way to use nuclear would basically be to carry on doing the sorts of things we're doing. So big power stations, largely on the coast, in communities that are used to nuclear, sitting there, hooked up to the grid, pumping gigawatt quantities of electricity into the grid. And you could go a long way with that. Our first move was Hinkley, next door to two previous generations of reactor. Our next move is Sizewell, again, an established nuclear site. And there are a number of existing nuclear sites which would be very suitable for that sort of development. And that will be helpful. But coming back to the point I made earlier about electricity demand skyrocketing as we use less and less fossil fuel, that is an approach that will run out of road. There won't be enough sites, and maybe we need things other than electricity out of our reactors. So that takes you to the small modular reactors, which are smaller versions of the big reactors, but still optimized to generate electricity. And they could be deployed, for example, on inland sites because their cooling requirements are much less. And then beyond that, you have this third generation, the advanced reactors, which would be deployed in different ways, because clearly you can't move 1,000-degree helium long distances. So if you want to use a reactor like that to drive a chemical plant, you really need to put the reactor next to the chemical plant. And both the small modular reactors put in different places generating electricity, and the advanced reactors put in different places driving industrial processes will be put in largely in places that are not used to nuclear energy. So there's a lot of work to do around what is called social license to operate, explaining what you're doing, why you're doing it, why you should be trusted by the host community. And that shouldn't be underestimated, because if you don't have that social license to operate, you won't operate. So putting these reactors in new places will raise new challenges. And also there will be regulatory challenges, particularly when you start, for example, putting a nuclear reactor next door to a petrochemicals plant. suddenly you've got co-location of hazards in a way we've not really had it before, and we need to understand how we manage that and how it's regulated. So as you become more non-traditional in your use of nuclear power, so you're going to raise a lot of these societal and regulatory questions that you haven't really had to think about so far.
Okay, and you mentioned the society thing at the beginning. Is it a permission-based thing? So in order to establish a new nuclear site, do they need permission from the host community?
They don't formally need permission, but if there is a long tradition of all sorts of projects in this country failing to proceed because actually they don't have this social license to operate. Social license to operate is not a piece of paper that you can wave at people. It is actually acceptance by the host community that what you're doing is something they're prepared to tolerate. And the one exception to all of that is geological disposal, which is around a volunteer community. But with new nuclear, there's no point in having volunteers, because if your petrochemical plant is over here and you want to power it with a nuclear reactor, you're very limited in the places you can put the nuclear reactor. It has to be close to the plant. So you don't have that flexibility that you have with geological disposal. There is a very clear planning and siting and permissioning process to be gone through. So it's very clear how you would build a nuclear reactor anywhere, whether it's a familiar community or an unfamiliar community. That process is laid down. But beyond that, for me, you do still need this wider trust, this social license.
Yeah, yes, of course. Yeah. And my final question to you, how did you get started in the field, and what is one of the most interesting things you've been working on recently?
How did I get started? I got a physics prize at school, a book, Man and the Atom, by a guy called Frank Barnaby, which caught my interest. I was lucky when I finished my first degree, which had very little negligible nuclear content. There was a PhD available, which caught my eye. That was about plutonium geochemistry, and I've been very lucky to stay in the field ever since, doing all sorts of things. And what's the most interesting and enjoyable thing I have done? I would say it's the 10 and more years I've been involved in the Centres for Doctoral Training, because I think they're brilliant tools for attracting really bright people into the nuclear sector, giving them a broad-based education, setting them up for a career in the sector, and after 10 and more years, seeing them out there now doing stuff that's really making a difference. So from the point of view of job satisfaction, you couldn't ask for any more than the CDTs.
Absolutely, I agree with you there, and I can vouch for the CDTs, but they're lucky to have fantastic lecturers like you, Francis. That's
creep.
Brilliant. Thank you very much for this.
Is that useful?
Yeah. Very useful, very useful. I've learned a lot.
Good. Okay, good. All right. Okay, well, happy to help. If you've got any questions, you know where to find me.
Brilliant. Thank you very much, Francis. Cheers.